Hello, my name is Bernardo Gonçalves and I'm a master's student of physics engineering at Instituto Técnico. I'm doing this video to present to you what is going to be my thesis work. Don't you ever wonder about what is the universe made of? Yes, I know it is made up of atoms, but even deeper, don't you ever wonder? Well, man has always been a curious wanderer, questioning and trying to understand what is around him. In his quest, man has come up with physics, where, with the field of particle physics, we try to understand the building blocks of the whole universe. The so-called standard model of particle physics is the best answer that man has come up with so far. So far, yes, so far. There are plenty of things that this theory is still unable to explain. But first, let us focus on what it can explain. The standard model describes elementary particles and the fundamental interactions of nature, apart from gravity, that is still waiting for a consistent way to be incorporated into our theory. However, this theory is able to describe matter particles and the other three interactions through what is called gauge bosons, that is, the force carriers. In this group, we have the gluons for the strong interaction that holds protons and neutrons together, the W and Z bosons that mediate weak interactions that explains radioactive decay, for instance, and finally, the well-known photon, the particle of light, that describes electromagnetism. Regarding matter particles, we have two groups, 6 quarks divided into 3 generations. We have here the building blocks of protons and neutrons, and 6 leptons, also divided into 3 generations, each one with a charged lepton, like our good friend the electron, and its partner, a neutrino. Still, we are missing a crucial piece, the Higgs boson, a particle predicted by the existence of the Higgs sector. No elementary particle could be massive if there were no Higgs sector in the standard model. Because of it, the electron and other particles gain their mass. However, neutrinos remain massless. So, you may wonder what is the problem with the standard model. Apart from gravity, it is able to explain nature in such a beautiful way. Well, yes, but an experimental evidence has changed the picture a bit. In the 60s, people were measuring the flux of electron neutrinos from the Sun produced in its nuclear reactions, but found a value that was between 1/3 and 1/2 the number predicted by the solar model. This revealed that neutrinos were far more interesting than expected. People came up to the conclusion that everything was right. Neither the measurements, neither the solar model were wrong. The neutrinos were the ones tricking us. Electron neutrinos that are produced in the Sun oscillate into other types during their journey, and so we detect less of them in the Earth than we were expecting. This indicates that neutrinos do have mass, and so physics beyond the standard model is needed. So we realize that the physical neutrinos that participate in the weak interactions are actually superpositions of states of well-defined masses. This rather strange concept is called mixing. In order to come up with masses for the neutrinos, one can relax a standard model assumption, the conservation of lepton number. And so, a Majorana, due to Mr. Majorana mass matrix for the 3 neutrinos, can be constructed into our theory. We can assume that, at a high scale of energy, where these masses are actually generated, the 3 neutrino masses are degenerate, that is, all the same. It is then possible to radiatively correct this matrix, bringing it down to our energy scale. With it, we can calculate all the mixing parameters and confront them against the values that neutrino oscillations experiments are giving us. This whole procedure has been done for the standard model, where the Higgs sector is minimal, but it failed in reproducing experimental data. But there is no fundamental reason to assume that this sector must be minimal, that is, with just one doublet. Well, what is a doublet? Think of it as a mathematical structure, a row vector with 2 complex entries. The simple extension of the Higgs sector is the addition of just one other of these doublets, giving rise to the two-Higgs doublet model. Here, the possibility of neutrino mass degeneracy at a high energy scale is still open, and I'm going to investigate it in my master's work. Can this open possibility lead to the observed experimental mixing parameters? This will be my quest under the supervision of Prof. Filipe Joaquim. Thank you for listening.